Yeah, thanks, Filippo. So thanks to the organizer. It's very nice to be back here, and nice to meet all of you. So I guess you must be pretty exhausted after I guess 7 days of lectures. So uh, so in this set of lectures, we will talk broadly about non-equilibrium matter, right, and entanglement. And some of the themes we will touch on would be thermalization, entanglement, and many-body localization. And I think, like every topic that has been covered in this school, it's a lot to cover. So most I can hope to do is to convey sort of why, what are the questions, why they're being asked now, right, and what are the key ideas, how they're connected. So I hope this at least gives you, a broad idea of the field, right, and then maybe inspires you to explore more, right? So be ready that sometimes I will try to convey the intuition rather than really trying to systematically derive something, right? But of course, and another thing I want to ask you, so please don't hesitate to interrupt me, because this way I can adjust the pace, if I'm going too slow or too fast, right? So I will very much appreciate your feedback. And also in terms of asking questions, also please don't hesitate to ask during the lecture, after, or shoot me an email during or after the school. And so let me start. Let me start with sort of invitation to the topic, right? And just what inspired this set of questions. And really, largely, some of these are not exactly new questions, right? But the reason for strong interest now is experiments, right? Which, this wave started with attempts to control synthetic quantum systems for quantum simulation. So, and let me abbreviate quantum, because there will be a lot of quantum, so Q simulation. And probably the first system which really, has been used for quantum simulation, these are systems of ultra-cold atoms in optical lattices. Right, so this started with trapping and cooling, laser cooling clouds of atoms, realizing Bose-Einstein condensate, right? And then also, right, so you have a bunch of lasers and many clever techniques to trap and cool atoms so they can, for example, Bose condense, right? And then other lasers are used to create standing wave potential, right? And that creates an effective potential for your atoms, right? So a priori, you expect standing waves to give you periodic, right? Periodic lattice, sort of like in a crystal. But turns out you can do a lot more, right? Because you have this amazing tools of quantum optics. And these systems are therefore extremely tunable. Right, so you can think of atoms, for example, each of these, you can be in the regime where each of these minima has, just a few quantized states, right? So then really it starts looking like a crystal because atoms can tunnel between these minima, right? They can interact when they come together on the side, so you expect general interactions to be local. And by tuning strength of your lasers, tuning wavelength, you can do a lot of things, right? So you can tune hopping, interaction. You can change the type of lattice you have. Also there are tricks to control actual dimensionality of your lattice, right? So you can study 3D, 2D, or 1D systems. There is more, right? There are also ways to introduce disorder. So making essentially adding a random potential to this lattice, and of course even this is only a part of it, right? So there are also, for example, here I'm talking just about a Hamiltonian system, but you can also even engineer dissipation to a degree, and that's, I don't know if maybe Peter mentioned that. Engineer dissipation. Right, and this gave rise, so this was, perhaps first demonstration of a many-body model in an optical lattice, and the quantum phase transitions between Mott insulator and the superfluid came in 2002 from the Munich group, right? And that sort of started, or really started this field of quantum simulation, and idea that has been, very sort of powerful, influential, and still guides many of the quantum simulation efforts, is that idea that you have the systems give you sort of a way to realize artificial crystals with the Hamiltonian, which you understand relatively well, right? So these are sort of conceptually pure models, right? Because it's not like a real solid where you have a lot of stuff that you don't control, right? You can have impurities, you can have phonons, right? You don't exactly know what your Coulomb interaction, how it looks once you try to write an effective model, right? Because you have a lot of orbitals that you do not fully understand always, right? In contrast, these are systems of atoms, right? They're, you know well how two atoms interact, how lasers, right, what type of potential they would create. And, people had this idea, okay, maybe we can go back to difficult questions about strongly correlated systems, right, and solve Hubbard model, right, and maybe learn something about high temperature superconductivity. Right, so for example, you can imagine that this can help you understand some strongly correlated models. And 20 years later, probably even Hubbard model has not been solved, let alone there is in a way another question: how relevant is Hubbard model to high temperature superconductors, right? And here, here quantum simulators would be relatively helpless, right? Because they simply, by nature, they are very different from real materials. Right, so and it doesn't make them less interesting. They're actually just new types of physical system. Right, new. And one big difference is that these things are just hanging there largely in vacuum, right? So they don't have a phonon bath, right? There is no external thermal reservoir. Right? So first of all, there are no phonons, and at least for a relatively long time, you can view them as isolated from an external, from a thermal bath. Right, so here, isolated is a keyword. And then there are also, right, there is also another important difference that here, Hamiltonians are broadly tunable, right? So you could say, well, I can also sort of program them to have this or that Hamiltonian. Of course, I cannot do anything I like, right? There are certain building blocks we have, atoms, lasers, right? How atoms scatter determines interaction. And another important difference is that actually the systems, right? So if you think about the length scales, right? These are wavelengths of light scales, right? They're large compared to spacing, latest spacing of a crystal. So these systems are very dilute, and their time scales, right? Their dynamical time scales are long. And here, let me add that you can control the Hamiltonian, and you can also control initial state. Turns out in these systems, so programmable Hamiltonians and states. Well, let me say initial states. And so, this makes them very different, but also, it makes them very well suited for studying non-equilibrium phenomena. Right, so all of this allows you to study non-equilibrium dynamics of isolated many-body systems. Right, while in contrast, in a metal or semiconductor, of course, there has been also a lot of progress in doing non-equilibrium physics, right? But their time scales are extremely short, and it is much harder to, probe intrinsic dynamics of your interacting system before it thermalizes. Although, that field has been really also developing very rapidly. Now, what the systems also offer is new kinds of experiments, right? And new types of probes. Right, so new probes and setups. Right, because for example, in solids, we are used to measuring responses, right? So we always think about conductivity, right? Heat capacity and things like that, generally, right? What we learn in a condensed matter course. While in synthetic systems, often measuring this is actually difficult, but instead what is natural is, right, in synthetic systems, in contrast, you have quantum quench setup, which is essentially, it's a very general, right, very general idea that you can initialize your system in some state you can prepare. So for example, I can place, atom in an optical lattice on every other side, right? And that would be my initial state, psi at time 0. And then I can, for example, I start out the system with Hamiltonian being such that these potentials are very deep, so atoms cannot tunnel, right? And then I suddenly make the lattice, less confining, right? And that starts generating dynamics, right? Atoms can hop around, interact, and evolve with the Hamiltonian, right? With this Hamiltonian, and then this creates some entangled state, which I can then image, right? Using tools of quantum optics. And over the years, right, in terms of experimental techniques, the systems really evolved. And for example, you can characterize the state with a single site resolution, right? So you can really go and see what are the probabilities of getting different configurations of atoms in your optical lattice after a certain time. Right, so you have single site resolution here. Right, so you can really watch in real time at least a large class of observables of what the systems do. So in the technology for doing that for cold atoms is called quantum gas microscope. So any questions already now? And so cold atoms were perhaps the first system which allowed to do these types of experiments, right, on a relatively large scale, but it is by far not the only one, right? There are other very different kinds of synthetic systems, right, which also, which offer other advantages, other platforms. Right, and here, for example, I can mention trapped ions, which was also an early platform for quantum simulation. You have superconducting qubits, superconducting qubit arrays. And so, recently there has been also a lot of exciting developments with Rydberg atom arrays. And as I said, each platform, in a way, is naturally suited to realize a certain class of Hamiltonians. Right? It's not exhaustive, right? So, for example, trapped ions allow you to have long-range interactions, while with cold atoms, interactions are naturally local, right? Because atoms scatter, and they have to really come together to interact. And recently, right, so of course, this idea of studying non-equilibrium dynamics has been very fruitful, right? But recently, it also perhaps acquired another dimension related to understanding computational complexity. Right, because in a way, original motivation, inspiration for quantum simulation is that quantum many-body systems are hard, right? Hard computationally because Hilbert space grows very quickly if you have a many-body system, right? And therefore, really understanding how difficult is a given time evolution or a given task, right, really came into focus in recent years, and that was, largely guided, inspired by really serious attempts to make quantum processors, or, sometimes one can use term digital quantum simulators. As opposed to analog quantum simulators such as cold atoms, right? So analog just refers to the fact that there is some, right, some natural Hamiltonian which you can tune, right? So, but that's some, you really use another physical system to encode some model, right, or emulate another system. While a quantum processor is something quite different, right? Really, so what you try to imagine is that you have some, elementary building blocks such as qubits, right? And let me run time, along x direction, right? So you have qubits and you control your system so well that you can keep them separate when you want to, and then you can apply, unitary operations to pairs of these qubits, right? So I can say, well, I can always apply some entangling unitary to qubits I and j, right, from some set, right, set of gates which is universal, such that I can eventually encode any, any unitary many-body unitary transformation by combining, single qubit and two qubit gates. Right, so here you see that these systems are very different. So here, you think about the revolution in terms of such quantum circuits. And right, and not Hamiltonians. Now, of course, if you really made a machine like that, you can encode, right? You can always encode any Hamiltonian you like, because you can always just go and say, well, you have some, if you want to encode some Hamiltonian, typically Hamiltonians we care about are sums of local terms, right? So it's some sum. For example, if I have a two-body Hamiltonian, so I have sum of pairwise interactions, right? Where H just acts on qubits I and J. And then if I want to encode evolution as a quantum circuit, so what I'll do, I'll just break it into product of small, right, of small steps, time steps, and then each step I can approximate by saying that this is product e to the I hij delta t, product over ij, to power t over delta t. Right, so, and each one of these is just a two-qubit gate. Now, of course, in practice, right? In practice, current machines like that are not, they're far from perfect. They're, very, very advanced at this stage, but still there are errors you're making, right? So, often you're better off at the current stage of doing analog quantum simulation rather than digital. That said, of course, here, this offers a lot of new opportunities, right? You can really, really control design many-body state that you're dealing with, right? And this, one of the questions that really came into focus, right, is this issue of finding quantum circuit, finding experiments, or no equilibrium evolution, which would represent quantum advantage, right? So really using this device to solve something you cannot solve otherwise. And non-equilibrium dynamics is also very interesting from this point of view, right? Because as we will see, actually, naturally, non-equilibrium evolution makes your state very entangled, and entangled states are hard to describe. So, okay, let me pause for a second and see if there are any questions. Okay, so then, right, let me start formulating some of the questions that we would like to answer. Right, so we can now write down a couple of simple models which are nevertheless very general. Right, so as a first example, I can consider atoms living in an optical lattice, and I will say, well, let's say tunneling is suppressed enough that I can limit myself to just tunneling between nearest neighbors. And let me also consider atoms which don't have spin. So for example, spinless fermions. And I can write a general Hamiltonian with nearest neighbor hopping. And I will also add interaction. And so since, in this case, my fermions are spinless, I have to stick to nearest neighbor interaction, right? Because they're not, by Pauli principle, they cannot come together. And so in writing that, what I'm doing, I am saying that other quantized levels in those wells are very high up, so I don't go there, right? It's too energetically costly. So I'm limiting myself to atoms living in the lowest bound state of each well. Right, and here Ni is the occupation number on site I. Right, and then what I can also do, what experiments actually can do, is adding random potential. So here on-site potential epsilon I, so can be made random or quasi-random, right? So epsilon I can be drawn from some distribution. So let me not worry about the shape of this distribution, but just say that it has some typical variance W, which I can tune. Right. Another type of model which is quite relevant and also conceptually simple are models of interacting spins. Spins 1/2. Right. So I can think, for example, of a magnetic system spins 1/2, and I can start, right? I can start with so let me call Pauli operator sigma. Right, I can start with a Hamiltonian just of the SU2 symmetric Heisenberg model, right, nearest neighbor Heisenberg model, and right, so that would be just a Heisenberg model, and then I can also add a random field in the z direction. Right, so that would be also disorder. And here, actually, for both of these models, we can consider a quench where you initialize the system in a simple non-entangled state, right, a product state. So for example, as we already said, atoms sitting on every other site or something like that, right? Or spins initialized in a product state where each is pointing, up or down, right? So let's say I have psi of 0, which is up, down, or some, something non-uniform if I want to. And then we can ask, so what would time-evolved state look like? Right, so in particular, whether under this isolated dynamics, whether the system would reach a steady state at long times, how is it approached, right? To the steady state, right? Of course, a very natural question whether this interaction would lead to effective thermalization. Or maybe there are other possibilities, right? And in a way, right, so one very sort of high-level question we can ask, what are universality classes, right? Universality classes of the types of steady state you can reach in terms of approaching steady states and so on, right? So universality classes of non-equilibrium dynamics. And yeah.
When you say universality class, you mean that you reach that state independently from the microscopic details of the Hamiltonian or from the initial state?
That's a good question. So rather, I want to ask what are the broad possibilities, right, for the type of steady state and how is it correlated with the initial state?
And if you change the detail of the Hamiltonian, adding, I don't know, new relevant terms, you will reach the same steady state, or you are
yes.
reaching another steady state?
That's an excellent question. Right. So you would, I think you can ask two questions, right? You can ask whether by perturbing your Hamiltonian, this completely changes your long time steady state, right? Or you can ask whether indeed the steady state is not sensitive to that perturbation, right? And I think I will ask somehow both questions. Yeah, but that's a good question. So for me, very loosely, I would say that if I have a space of Hamiltonians, right, I am interested in finding at least, some regions where I can observe certain kind of dynamics, right? Now, that said, there are also cases where you have, strictly speaking, if you're thinking about really long time steady state, you get something anomalous if you have points or lines, right? For example, if you think about one-dimensional integrable systems, right, where integrability gets broken if you consider a very large system and very long times, right? But still, to me, those examples would be interesting, right? So understanding what are the time scales and sort of for how long I can see this anomalous dynamics. Pardon question. Thanks, Andrea. Well, so I will, especially when I talk about many-body localization, bulk of what has been done is about 1D, right? But we can think about higher dimensions, right? Of course, I would have a lot less to say in higher dimensions, right? So, I mean, as it often goes, I think we know the most as far as many-body localization goes, either in one dimension or in infinite number of dimensions, right? When you have full connectivity, right? That said, some things would be very robust, right? So, for example, when we talk about thermalizing systems, right, that's extremely robust and it would work in more or less any setting. Okay, any other questions? Okay. Right, so that's one high-level question we can ask. And here, often we would sort of focus on a case that you could say is maybe not very relevant, for example, for condensed matter systems, right? So we would think about states which are very highly non-equilibrium, right? Where, for example, when you look at this Hamiltonian, right, you always, in condensed matter context, you think about ground state excitations. So we would be very far away from it. We would be in the regime where we put order 1 excitation, right, per whatever site or per mode into the system, right? So we'll be in this limit of, where temperature is effectively very large, right? So this, in a way, these details of what's going on near the ground state would not be very relevant, right? Just to try to gain an insight into this, right, very general question. Now, of course, it does not end here, right? And there are other question that we can ask, right? And ultimately the hope is also to use these capabilities of bringing matter out of equilibrium in a controlled way to essentially find new functionalities or new properties out of equilibrium. And of course, here you can imagine something like if you drive your system in a controlled way, right, you bring it to an equilibrium steady state, which, for example, becomes superconducting while your original system in thermal equilibrium was not, right? So that's a little bit, type of a thing you can try to do. And of course, this would be in a different regime compared to this very highly non-equilibrium dynamics, right? Because here you would want to stay not too far, maybe from some low energy state. Right? So you can induce desired order, for example, by driving. And then another line of research is to find instances of non-equilibrium dynamics, non-equilibrium behavior, which would be, where there would be room for useful quantum advantage, right? And we can use, for example, we can use quantum processors to learn something new. And here, right, this actually, so let me just mention, I will not talk too much about computational methods, right? But of course, this goes hand in hand with advances in classical computational methods, right? In particular, tensor networks, of course, is a a very nice set of tools to which is useful for simulating quantum dynamics. Classical computational methods. Right, in particular, tensor networks. And I would say these are three main themes, and I will mostly cover this part and maybe touch upon this last part. And also, hopefully on Friday, we can talk a little bit about the experiments that are being done now, right? So such that you just get a flavor. Of course, it's, I won't be able to cover a whole lot, but just to give you a flavor. And here, so I guess we started a little bit late, so shall we? Yep. Or maybe just to get back on schedule, let's take a break now, right? So it's 12:02. Yeah, and then we can resume in 10 minutes. So 12. Yeah. But in the meantime, yeah, if you have a question, please ask. If not, after the break. All right. So to start answering especially this first question, right? So let's make some simple observations, which I guess Pasquale already covered, but let me just tell them once again. Right, so of course, if we manage to understand dynamics, if we manage to understand the eigenstates, that's already a big part of a job, right? So in principle, I can find a basis, right? A basis where my many-body Hamiltonian is diagonal, right? And alpha runs from 1 to d capital, where d is the Hilbert space dimension. Space dimension. Right, so for example, for system of n spins 1/2 or n spinless fermions on a lattice, d is 2 to the power n, right? So it grows exponentially with number of degrees of freedom, right? And then, so if I understand the eigenstates, then to describe the behavior in a quantum quench, so what I'll do, I would expand my initial state psi of 0 in terms of eigenstates, right? There is some set of coefficients which defines psi of 0, and then evolution becomes, right? I simply need to multiply this by phases, right? By time-dependent phases, which are different for each eigenstate. Now, of course, the state, right, is huge. So the way we probe and characterize it by observables and generally observables are local, right? So what we can do, we can measure some operator like sigma z on one of the latest sites, or it can be, for example, some sigma I x sigma jx over some set of spin pairs, right? But the crucial thing is that there would be order n terms here, or maybe order n squared, but not that many, right? And each term here would be local, right? Involving a finite number of spins. So, and I will call loosely this local operators, or local observables. And if I will need to, refine it, so we'll do it as we go. But what is crucial, so things you cannot generally measure in the lab for as your system gets bigger and bigger are very complicated superpositions, right? Where, for example, you have a nu 1, nu n, sigma 1, nu 1, sigma n, nu n. Right, so such things, right, generally very non-local, so yeah, you don't have an experimental way of measuring them. And right, so we will be thinking about local observables, and then so you can measure how in a quench experiment you can measure how the expectation value of O evolves, right? So it's just psi of t O psi of t, and I can express this in terms of time evolved state here. So I have sum over alpha beta, C alpha, C beta star, I beta, O alpha beta, where I defined, right, I defined O alpha beta, which is beta O alpha, right, and this is matrix element of the operator O between two eigenstates. And then, also, so it will be convenient for us to rewrite this sum by separating a term where alpha equals to beta, right? So, and where diagonal matrix elements would enter, C alpha squared or alpha alpha, and then sum over off diagonal matrix elements where I have these phases and right, so here diagonal matrix element contribute and they're off diagonal. And so, and therefore, a priori, we would like to gain an insight into three pieces, right? Three properties. So first of all, excited eigenstates. And excited for us would mean that these states have extensive energy essentially, right? Those would not be states where I have a ground state and I put, three magnons on top of it, but where I put some density of magnons, for example. Right, so here it would mean finite energy density above the ground state. Then another important piece are properties of matrix elements. And finally, right, the set of coefficients C alpha. So how is your experimental initial state, right? Typically, that's a relatively simple state. How does it decompose in terms of the eigenstate of your system? And so, and what we would find, right, is that there are actually several quite different possibilities for, how this can behave in a many-body system. And here, going back to point that Jerome brought up, right? So one can be, one can ask whether truly in the infinite time limit, your system, reaches a particular kind of steady state. But you can also ask, what does dynamics look like for a sufficiently long time, right? And so to separate the two, first one would be really a phase. You could say dynamical phase of matter, and here let me call it dynamical regime, right? When you see particular kind of dynamics for maybe a very long time, but not truly infinite time, as your system gets bigger and bigger, right? So let me separate these two, and then we would see that there are a few scenarios, few regimes, right? So I'm thinking about this, about our quench setup. And so depending on the properties of your Hamiltonian, so first option is thermalization. Right, where at long time, your psi of t would effectively have thermal observable, right? So local observables would look thermal. Thermal local observables. And in this case, after this has happened, then you can use statistical mechanics, right? Which, of course, we know a lot about. On the opposite end of the spectrum, we will have many-body localization, which crucially, so to get many-body localization, you need typically strong disorder. And here, your state psi of t would remain non-thermal. And what is even more interesting, so it will retain memory of the initial state of the system. State psi of 0, right? And in this case, and of course this should be contrasted with thermalizing systems, right, which forget their initial condition. Meaning you would not be able to recover it from measuring local observables. Of course, there is your time evolution is unitary, so if you could measure, very non-local observables, you could see that these were two different states, but effectively because of thermalization, all the local observables would look the same. And this, right, so, once you don't have thermalization, then of course your dynamics, right, your dynamics does not bring you to state described by statistical mechanics. And that leads to some new interesting possibilities in terms of having distinct, for example, behavior with different symmetry and so on, right? So, and this leads to new non-equilibrium behavior. And let me loosely say phases, right, without insisting that this would be something that survives at infinite time in a limit of infinite size. And in a way, we would see that many-body localized systems are maximally non-thermalizing, right? They would be sort of very, very non-thermalizing. And there are also, scenarios which are in between. So in particular, there is scenario of pre-thermalization, where your system would thermalize thermalize eventually, right? But it can have some integrals of motion for a very long time, right? So you could say this is regime of parametrically slow thermalization. And in this regime, your system, tends to have some long-lived approximate integrals of motion, right, which are quasi-conserved, but then eventually they decay. So quasi-conserved, conserved integrals of motion. Let me abbreviate it IOM. And there are different, different physical mechanisms of being in pre-thermal regime. So you can, for example, you can start from an integrable system, right, and then consider weak integrability breaking. Turns out there are also other ways to get pre-thermalization when you have, especially in your latest model, when you have two energy scales which are highly incommensurate. For example, if you have Hubbard model with large on-site interaction U, turns out there will be a pre-thermal integral of motion, right? And I will talk about it probably in the third lecture. Huh? No disorder, right? You could have disorder. It's not, these are very general, but yes, generally no disorder. Right. Right, and this has actually, so this mechanism has, some interesting applications to robust edge modes and things like that, which, okay, hopefully we'll touch upon. And then there is yet another interesting scenario, which goes under the name of quantum many-body scars. Many-body scars. And these are examples where you have, generally your system is thermalizing. Also here, no disorder is necessary. But there are special initial states, psi star of 0, which thermalize very slowly, or maybe don't thermalize if you are, in a solvable model, right? Which show, let me say, anomalously slow thermalization. But here, for other initial states, you would see normal thermalization, right? And there will be no surprises. And okay, so our goal will be to gain some intuition about this, right? About these scenarios, regimes, right, and underlying mechanisms. And ultimately, what we would use quite a bit is this idea of integrals of motion. Right, integrals of motion. And we would see also that there is a way to really learn quite a bit about many-body localization by thinking about conserved quantities, integrals of motion. Of course, both the mechanism and stability would be quite different, for example, in this example and in the pre-thermal regime. And quite a bit of, yeah. Well, so I would include it broadly here. Right, but yeah, you're right. Of course, and much of the language, right? For example, I think there has been many early works on pre-thermalization exactly in the context of breaking integrability, right? But generally, integrable systems are, you need fine-tuning of your Hamiltonian to get them, right? And therefore, if I consider a general Hamiltonian, I would put them in this category. So, okay, any other questions? Yeah. Yes, that's a very good question. So here, I think you can have different situations. I'm talking more about a situation where you just have a rate, right? You have an approximate integral of motion, but the rate of its decay, right? So I have some integral of motion, right, which almost commutes with your Hamiltonian, right? But it doesn't commute slightly, so it will decay according to normal, golden rule decay, right? But with a rate that I can control, and this rate can be, for example, exponentially small in some parameter, right? Now, I think most integrable systems would not be like that. Their rate would go as a power, right? Power of the strength of your perturbation. In some examples, yes, right? Yeah.
Yeah, I'm just interested in why is not decriminalization included in criminalization? I would say this is just a special case of criminalization.
It is, but it leads, so, so imagine if you have a situation where you can use prethermalization to really make this integral of motion extremely long-lived, right? Then it would have experimental implications, right? For example, some edge mode can be very long-lived out of equilibrium, right? And that's interesting. Now, from the pure, here, yeah.
Define criminalization as in time goes to infinity limit. Then if it thermalizes, I would put it into the same basket, right?
Right. I think if one wants to, so here, a lot depends on the, let's say, on the definition, right? If I really ask, well, does a system thermalize as I take system size to infinity and time to infinity, right? Then it very well could be that all of this, especially in abelian higher dimensions, they all eventually thermalize. But still, if it happens on the time scale, 10 to the 10, right?
Here we just distinguish things that we can measure.
Right. So here we're talking about regimes, right? About regimes, right? And but it's a little bit, if you think about, experiments often always happen on a finite time, right? What you care about is that your experiment does something during this time, right? So here, but that's why to emphasize that here I wrote regime and not, right, not a phase. Yeah. Right. Right, but it's important, I think it's important to also keep in mind that indeed, there are a lot of interesting questions about intermediate time dynamics, right, and long time dynamics, but maybe not infinite time dynamics. And even you would see that, for example, this question, about eventual fate of many-body localization at extremely long time, extremely large system sizes, it's almost, gets into the regime where either you come up with a proof, right, or you don't get an answer because, well, proof or proof that it's unstable or it's stable, right? Just because it's in the regime which is extremely difficult computationally because you would need infinite system size, right, and infinite time, and it's far, far out of any reach of experiment conceivably now and for the next 100 years, right? So it's almost in this regime of unfalsifiable unless you really have a mathematical proof that everybody agrees on, right? So in a way, I think it's an important problem, for mathematical physics, right? But our friends in mathematical physics generally say that it's too hard, and they're better equipped for proving easier things for few particle localization and so on, right? But I'm sure it will be resolved at some point also. Right, but the only way I see there is really, we are sort of mathematical physics, right? While here, in these regimes, you can get rigorous results and give bounds, right? And they have direct experimental relevance. Okay, any other questions? Yes, so exactly. So here, in a way, there is a question, how should you define ergodicity in quantum many-body systems, right? And generally, I would say thermalization and ergodicity have been used kind of interchangeably here, right? And I think right, so you would see that thermalizing systems are called ergodic. Now again, I think especially community that works on ergodicity in classical systems might have a more refined view of what ergodicity should be called, but I think in this context we can use them interchangeably. And therefore, you would see that, for example, many body localized systems are called ergodicity breaking, and things which are in between, like quantum many-body scars and related things are often called weak ergodicity breaking. Okay, any other questions? Yeah, Jerome? Yes. You mean for the isolated or for Lindblad? No. I think this is a very sort of very alive area, right? So for example, here I think the story of quantum many-body scars is curious because it came, and again, in retrospect, I think there has been some examples from theory which are very much related, but the way it came into focus, so there was an experiment with Rydberg atom arrays done in 2017, right, by the Harvard MIT group. And what they found, they realized the model without disorder, and then they saw that certain initial conditions were thermalizing much, much slower, right? So it was really, one of the first surprises, right? Really of something unexpected from a quantum simulation experiment, right? So I would say I completely leave open the possibility that there is more stuff, right? It's just these are some of the examples that we know so far. And then I think also, indeed that's a good point. So here I'm focusing so far on isolated system dynamics. So you have a Hamiltonian, or maybe you have a periodically driven system, so Floquet system, right? But then there is of course a whole other dimension of what happens once you add dissipation, once you study Lindblad evolution, Lindblad many-body evolution, right? And there generally you expect that you would come to some non-equilibrium steady state, right? You have a driven dissipative system, right? But the types of them, I think there is a lot of room to explore, and whether the steady state is unique, whether you can have some dynamics taking you between steady states. I think that's pretty much, yeah. Integrable systems.
Yeah, it doesn't normalize.
Well, here that's exactly the question. Well, I will draw the line again, and I think this line is, one can discuss where one should draw this line, right? But I would say, for me, many-body localization would be a case where it is disorder which leads to integrals of motion, right? While for integrable systems, it would be, beta ansatz, right? Or right? So that would be just for me a slightly different mechanism.
So different mechanism that lead to integrals of motion.
Yes, yes. And in this case, so we would also see that integrals of motion are very different, right? But at some high level, I think that's exactly right, right? That ultimately you need to understand approximate integrals of motion and their lifetimes, and then you can, in a way, what your system would naturally do is just sort of dephase, right? Dephase states which have different values of integrals of motion, right? Leading to, for example, generalized Gibbs ensemble, which I guess Pasquale already brought up last week. But the way integrals of motion emerge and how what determines their robustness and their decay, so there you would see very different physics. I think that's what something we keep in mind. That indeed, at some level of organizing principle, I would say it's integral of motion, their lifetimes, and all that. But the underlying physics and how you get there can be different. Right? Okay, good. Any other questions? No? Yeah. Okay, so then let me mention that really what has been interesting about this field is that it sort of brings us to the regime which is far from where powerful methods that we are using, for example, in condensed matter and field theory, have been developed for, right? Because we typically think about a field theory, response functions, and things like that, right? So here we are going very far away from equilibrium, right? So we don't even have a starting point of having field theory description. And but what has been very insightful is really thinking in terms of quantum information, tools, ideas, right? And in particular, thinking about entanglement. And I think so. What we see more and more is that this line of research, so it really interacts a lot with condensed matter physics, quantum information, quantum computing more and more, right? And also with some interesting connections to let's say mathematical physics, right? And why entanglement matters so much? So let me spend a few minutes discussing this link between entanglement and complexity, right? Because if you take a step back and say, well, we are trying to describe some, very excited state of, for example, a spin system, right, where I have n spins, and I have 2 to the power n basis vectors. So some, let me say S1, Sn, where each Si is up or down, or 0 or 1, right? Then to specify my many-body state, right, I would need to a priori keep track of all these amplitudes, right? So I need 2 to the power n amplitudes parameters to describe a state, right? And of course, this is completely insane, right? So you would never, you would run out of steam at about, 30 spins or so, just because you would run out of memory. And then you can wonder, how come we know so much about many-body physics, right? So if the things are so complicated, right, it doesn't add up. And here you can ask a question, okay, how really quantum is a given many-body state? So you can ask how non-classical is a many-body state. And here, here entanglement turns out to be very informative. And to quantify entanglement, so I think also that came up already, but let me just remind you. So to quantify entanglement in a state psi. So and here I will stick with pure state, right? Although of course defining entanglement of mixed states is a separate, very interesting issue, right? Which brings you more to quantum information world, but let me not go there. And what I would do, so let's say I have, you give me a state psi, and then what I can do is look at different subsystems. A, for example, I can choose a block of spins, adjacent spins of some size, or I can choose two different regions, right, which are not necessarily connected. And then I have my system S. And then I can look, right, I can look at the reduced density matrix of rho A, which I get if I trace out degrees of freedom in the complement of A. Right? So I can just look at the state of A, so it's described by a density matrix, and the more it is mixed, right, the more my state is entangled. And the way to quantify it is so I define entanglement entropy of A, which is just von Neumann entropy of the reduced density matrix. But it's always defined with respect to a subsystem and a state, right? And in a way, it tells you if I were to measure complement of the system, what would be in some basis, right, in the right basis, what would be the entropy of the outcomes that I get? Right? It would be something like that. And here, of course, if the size of my block of spin is L spins, then the maximum, right, maximum entanglement I can get is L log 2. Right. Right, so it can scale proportional to the number of spins in this system, right? And the remarkable fact that really sort of gives a basis for tensor network methods is that states with low entanglement are easy to describe classically. In the sense that you need a lot fewer parameters than this full, Hilbert space dimension. Right, and here you can sort of guess it from the fact that if you have a product state, you can specify a product state by only number of parameters proportional to n, right? Because I need to specify, 2 amplitudes for each spin, right? So I have, 2n, right, or 3n parameters. For example, product states, you need order n parameters. Right, and turns out that this is a lot more general and really a way to tell whether your state has low entanglement or high entanglement. What you need to do is to look at the scaling scaling of S entanglement of A as a function of L, which is the size of your subsystem, right? And let me denote boundary of A by dA, and then I will, the volume of the boundary would be just like that, absolute value of dA. And low entanglement means that S entanglement of A grows proportional to the volume, right? Volume of the boundary. And this is called area law entanglement or boundary, right? Boundary law entanglement. And so you can picture that if I have a very large subsystem, right, still entanglement lives near the boundary, right, and the degrees of freedom inside maybe they're entangled with each other, but not with things far away. And turns out that these states you can approximate efficiently, right, generally approximate very well, right, using number of parameters which is scales polynomially with the number of your spins. And so, and generally the ground states up to some examples, so are in this category. So ground states of local Hamiltonians, most of them would be in this class. And then on the other side of the spectrum, you have states where entanglement goes proportional to L, right? So it's volume of the system itself. And these states are, you expect them to be very, very entangled, right? And they're far, right, very far from product states. And generally, right, at least, most generally, you would not be able to compress them efficiently, and the number of parameters would be exponential. In the system size. And non-equilibrium states, relatively quickly get into this category. So after some time of evolving the system, right? So non-equilibrium states get into this category. And the way to going back to the area law states, right? Technology to describe such states. This is tensor network. So for example, in one dimension, what you can do, you can represent these amplitudes, right? Amplitudes of the wave function you have there as so you have a bunch of matrices, right? And these matrices, right? You have matrix B, S, I, and to get amplitude of your wave function, so you need to multiply these matrices together, and then, okay, so you draw it like that, so Si is your index. And then you see that number of parameters you would need would be n times d squared, right, where d is the size of this matrix. And so, and this is the idea of, in one dimension, these are matrix product states. And that, really, this is a very powerful technology for studying ground states in particular of, right, of interacting spin chains and systems like that. So, yeah. Small a. Well, so this is, this depends a little bit on what you are trying to, you know, what is your measure of approximation? Yeah, but this is some number. This is just some number. Right, right, exactly. So are you asking why, intuitively, why should they be in this class? Yeah, yeah. Well, that's because, I mean, if I think about a ground state with a gap, for example, right, then I can define, right, so if I have a gap, I can define a correlation length, right, proportional to 1 over the gap. And then I say, well, stuff here is not, in this state, is not correlated with stuff far away, much further away than the, right, than the correlation length, right? So, and you can, you know, proving exponential decay of correlations when you have a gap is easier than proving area law entanglement. But in one dimension, you can also prove area law entanglement. But I would say it's, I mean, this intuition is very solid, right? So modulo some exceptions, you, please.
With ground states, we have this area law entanglement, and would we expect it for the first excited state, or how would we expect if we go up the spectrum to behave, or is it like continuous transition to the volume entanglement or stuff?
Yes, very good question. Well, so if you put, you know, imagine putting plane waves, right, on top of your ground state. So then you would say, well, you have one excitation, right? So it can be either in the left side or on the right side, right? So those states would still not be very entangled, but their entanglement would grow as you add more and more excitations, right? Yes, yes, yes. Right, right. And once you have, you know, once you have finite density of excitations, then you are in the, generally, you'll be in the volume law. With a prefactor, right, with a slope that depends on, you know, that depends on the density of excitations, right, energy density. And then once you are close to, you know, having once you have lots of excitations, right, it will be sort of a maximum possible volume law you can imagine with essentially with a prefactor proportional to log 2 or something like that. Another, yeah. Yeah.
So the things like we already know that all the problem with the fact that people cannot easily use tensor methods is because the A exponent in n to the A is much larger.
Yeah. So things get harder also. Indeed, in one dimension, a great thing is that contracting such states is very convenient, right? In 2 dimensions, there isn't such a, you know, useful, such a simple way exactly for the reason you mentioned, because you have a 2D tensor network, and then you have to start where you have to decide how do you start contracting it, right? And that can get challenging, and there are not as clean guarantees, right? So generally, it's a lot more expensive. What you have to do also in terms of this parameter d, which is the bond dimension, right? So there is also, you know, another power, you know, d to some power beta, let me say, right? How expensive it is contract, and how expensive is it to optimize over the tensors, right? Because there is a variational. Of course, this is a. You can start building variational methods from this, right? You can ask, okay, how well does it approximate my true many-body state? And then there is also a cost of performing this optimization, right? And indeed, 2D tensor networks, of course, there have been remarkable developments, also kind of conceptual, but numerically it's a lot more challenging. So when right. But here also, I think it's important to keep in mind that there is a physicist view, right? And then there is complexity theory view, right? Because indeed, maybe from complexity theory standpoint, all the correlated systems we are talking about are not that complicated, right? They're all polynomial. But thing is that, that's why I put easy here in, because we know that despite being in this areal regime, right, you have incredible richness of phenomena, right, phases, and which we don't have full control over, right? So, but that said, if you're asking really question about having quantum advantage, right, and something being truly, really hard, right, exponentially hard, right, that becomes relevant. And of course, this whole field of quantum complexity, that's also a very interesting field, but it's maybe focusing a bit more on, right, on this proofs of what is really hard, right, what is just hard because, for example, tensor network methods come up with polynomial algorithm with a very high power, which effectively makes it, right, makes it run out of steam very quickly. And okay, yeah, so we will use quite a lot, appeal quite a lot to entanglement properties of both eigenstates and how entanglement grows if you do a quantum quench. Right, so yeah, I think this was yeah.
Just regarding this question, if you take the Fermi-Hubbard into the state is area law or more than
I think it's area law. Yeah, I think it's area law.
The fact that there is this sign problem in the field you're simulating has not impact on this classification that you're doing.
Yes. So that's actually that's a very good point, right? So that indeed, right? This is somehow a different view of complexity, complementary to what you have in quantum Monte Carlo. Whether you have a sign problem to get to some get to some low temperature state or not exactly. And I think in terms of the relation between the two, I guess with the sign problem, often it is difficult to get a real estimate of complexity, right? So you know that your quantum Monte Carlo algorithm struggles, right? You're run out of steam, but in terms of really saying, okay, it is that hard, right? I need to sample that many configurations, right? I think it's more.
Take exponentially many configuration to get rid of the sign problem. You would think that there is something that would move from there to there.
It is, yeah, I think it's not very well understood actually, but it could be, right? It could be just that, you have, for example, if you think about some intricate model like Hubbard model, right, that your correlation length is sufficiently large, right, and then okay, so that becomes 2 to the power xi squared, done naively can be really, right, really limiting, right? So, but again, yeah, I think we will see more on these issues and better understanding, okay, how to further refine your tensor network ansatz, for example, to have fewer parameters, right? And in particular, yeah, indeed, I think this link with sign problem is very, very interesting, especially when we talk about dynamics. So, okay, any other questions? I think that's a good point to stop for today. Yeah.
I didn't completely understand
Well, generally we think about local interactions, right? And then ground states, right? Ground states generally belong to this area law, right? Area law class. So they are, so you can use this technology very successfully to approximate them. While with non-equilibrium, right? Non-equilibrium.
Hamiltonian can have long range interactions, but ground states still obey area law.
Yeah. Right. Yeah. Okay. So yeah, today we covered some, introduced some key ideas, and so next time we will look closer at thermalization, MBL, and pre-thermalization. So thanks, and I guess it's lunchtime.